Good morning. Welcome to NGSS Physics. Today we are going to be going over a little bit of planetary motion by going over the three laws of planetary motion as put forth from a scientist named Johannes Kepler. Now, Johannes Kepler lived a long time ago. He actually came before Isaac Newton, and he was a brilliant mathematician that just described how the planets moved. He didn't necessarily tell you why the planets moved or what caused that movement. That came later with Isaac Newton and Isaac Newton's laws of motion and his universal gravitation formula. The funny thing about Isaac Newton is all of the laws that Kepler came up with can be derived by using Isaac Newton's law of universal gravitation. And so he basically proved that Johannes Kepler was onto something and was correct. Now, if you make a nice observation of the night sky, you might notice that the stars, the moon, the planets, everything seems to rise in the east and set in the west. That's a general observation. And in Johannes Kepler's day, people believed then that the Earth was at the center of the solar system because it appeared that everything went around the Earth. And they pretty much thought that everything was going around in a perfect circle. Uh, One of his predecessors, Tycho Brahe, was a very precise scientist that took precise measurements. And when he did this, he realized that not everything was going around in a perfect circle. In fact, some of the planets seemed to go faster and slower at different times. And maybe they didn't go in a perfect circle, but they went in odd paths. And he came up with some odd types of solar systems in which there were epicycles. Upon even closer observation, another scientist named Copernicus said, what if we don't put Earth at the center of that circle? What if we instead put the sun at the center of the circle? And then it simplifies things back into those perfect circles again. And so everybody was quite happy until Johannes Kepler took a better look at the data and said, even if you put the sun at the center of the circle, things are not going in a perfect circle. In fact, Tycho Brahe, who took all of these precise measurements, when he died, Johannes Kepler got them and was able, through mathematics, to figure out that the path that planets were traveling were not perfect circles. And he basically looked at the path of Mars because that's the data that we had the most information for. And he figured out that instead of traveling in a perfect circle, Mars traveled in a shape that was called an ellipse. Okay, an ellipse is kind of like an elongated circle. What is an ellipse? Let's pause and talk about that a little bit. An ellipse is, like I said, an elongated circle, whereas a perfect circle has only one center. An ellipse will have more than one center, and it'll be stretched out. And the further those two dots are that form the center of the ellipse, okay, the more elongated that ellipse will be. In fact, the distance between one dot and the outer area is going to be the same on each side of that ellipse. It just so happens that in our solar system, one of these dots happened to be the sun. And that is the one that has all the gravitational attractive pull going on. This is the first law of planetary motion. Objects travel not in a perfect circle, but in an ellipse. And this is true for all of the planets, all of the moons, all of the objects that are out there in the solar system that are in orbit around other objects, including man-made satellites in space. All right, so let's describe a little bit about an ellipse so that we can understand a little bit of the other laws of planetary motion. An ellipse, because it's an elongated circle, has what we call a major axis, which is if you cut the ellipse in half, the long way, that would be the major axis, and it has a minor axis if you cut the ellipse in half. The short way, that would be the minor axis. It just so happens as an object is in orbit around um, the foci that is causing all the gravitational pull, at times it'll be closer to that foci, and that is called perihelion. So when Mars is closest to the sun, or the Earth is closer to the sun, we are in the perihelion portion of our um, orbit. When it is furthest, okay, away from that point that is causing all the gravitational pull, we're at aphelion. So perihelion and aphelion are two specific points in the orbit of an object. Um, and every orbit, because every orbit's an ellipse, will have a point at which the object is at perihelion or aphelion. All right, let's talk a little bit more about an ellipse. How elongated is the circle? That's called its eccentricity. Okay, for a perfect circle, it doesn't have any eccentricity at all. Okay, because it's not stretched out at all. As that circle gets stretched out, we say that is now eccentric. And the more stretched out it is, the more eccentric it becomes. Okay, we can actually calculate how eccentric a ellipse is by using a simple formula. The eccentricity is equal to c divided by a, where we call c the foci distance from the center, and a, okay, that's the foci distance from the center, and a is the semi-major axis, which is that right there. This is the way that Johannes Kepler calculated the value, because Johannes Kepler was using geometry, and he actually drew a triangle that looks like this in his right angle, because this semi-major axis line is the same distance that this line is right here, the hypotenuse of his triangle. Today, we can make this calculation a little bit simpler by just saying, well, this distance right here between the foci and the center is just 1/2 of this whole distance between the two foci. And this distance right here, the semi-major axis, is just 1/2 of the distance of the whole axis. So we could actually write a simplified formula that says the distance between the foci and the semi-major axis total, d, and we can get the same exact number for eccentricity. It's just a multiple. Let's pause right now and go to your formula sheet. The formula sheet's a 2-pager, and if you go to the second page, you'll see on the second side at the very top, you'll have Kepler's laws, and over here, you'll see what all of those variables stand for. So the one that we're talking about right here is this one right there. And the F is going to be the distance between the foci in an ellipse, and D is going to be the distance of the major axis. We could also get this using Johannes Kepler's way by saying C over A. So if you wanted to put that in there, you could as well. Okay, what do you notice as the E increases, or the eccentricity increases? Okay, notice that it gets stretched out further and further and further. In fact, theoretically, it can only go to an E of 1, and that would be a straight line. So an ellipse is any eccentricity between 0, which is a perfect circle, and 1, which is a straight line. Let's calculate eccentricity. Okay, let's say you have this particular ellipse. If we were to calculate it using Johannes Kepler's way, we would first measure the distance between one foci and the center. Okay, and we're going to be using the semi-major axis line. So this distance right here, and we get 4. And then 1/2 of the major axis, which would be 5, and we get 0.8. For our purposes, on the back of our formula sheet, we have F over D, which would just be the distance between foci, which would be this whole distance, which would be 8, divided by the major axis, which would be 10, and we still get the same exact answer. All right, which leads us to the second law of planetary motion. Kepler noticed that Mars changes speed as it orbits the sun. In fact, when it is at its closest state, which is perihelion, it seems to be going faster. And when it's at its furthest state, which is aphelion, it seems to be going slower for the distance that it's traveling. What he found out geometrically was the area, this distance, was a bigger distance than this distance, even though the planet covered it in the same amount of time. But if you did a little geometric formula and figured out the area in that triangle and compared it to the area in this triangle, he found out that the area was exactly the same number. And he called this law equal time for equal area law. This is the second law of planetary motion. As a planet moves, okay, as it's closer to the sun, it's going faster because the area, okay, this triangle is going to be a little bit shorter legs there. Whereas as it gets further away from the sun, it tends to slow down, but the area in each triangle remains the same. Equal time for equal area. The second law of planetary motion. All right, quick question. At which place is Earth moving the fastest? And at which place is Earth covering more distance? Well, if you know what the speed formula is, distance over time, you know that, oh, it is directly related. So it's covering more distance, it's going faster. And so the answer to both of those questions are A. A, it's closest to the sun, and so it's going faster and covering more distance, which leads us to the third law of planetary motion. Okay, in the third law, Kepler found that there was a relationship between the time it took a planet to go completely around the sun and the average distance from the sun. We're going to call the average distance from the sun R because it's kind of like the radius of that ellipse. And we're going to call the time it takes to go around the sun T because time starts with T. And he found that the relationship looked like this. The square of a planet's orbital period is directly proportional to the cube of the semi-major axis. And he compared all of the different planets in our solar system when he did this. And he came up with a very unique formula that looks like this. Now, this is only going to be true for that mass of the sun in the center of our solar system. Uh, because we're going to be using astronomical units and the year, that makes it that this whole formula have a certain constant. If we were to go to a different solar system, that solar system would have a different gravitational constant, and it would change these numbers slightly. But for the Earth solar system, the sun solar system, and the Earth, we can choose some numbers to make this a little bit easier to understand. Kepler's third law. If we decide to use the time for Earth as 1 year and call it 1, and then use the distance for Earth between the Earth and the Sun as an astronomical unit, because that's what Kepler called it, 1 astronomical unit, we can then calculate the time it takes other planets in Earth years or the distance that other planets are from the suns in astronomical units in relation to the Earth. Let's have the Earth's time and radius be our blue numbers down here. So if we change t down here, the blue t, as Earth's t, our time, to 1 for 1 year, 1 multiplied by 1 is just 1. If we then also change r down here to Earth's distance of 1 astronomical unit, and 1 raised to the third power is just 1, we get a formula that looks like this for all of the other planets in our solar system. The t and the r for all the other planets can be solved using this simple formula. Yeah, notice that the ones cancel out because anything divided by 1 is just itself, and we can simplify it into looking something like this. This is also on your formula sheet. Here it is, just like that. And remember, this is only good when we use a time in years and a r, or a radius, in astronomical units. If we were to use a different unit for time and a different unit for distance, that would change this formula slightly, and we'd have to bring those blue letters for Earth back into the equation. But let's just use astronomical units in years for now. Let's take a look at a sample problem. When we compare the orbits of the planets, we get something that looks like this. Obviously, Earth is 1 astronomical unit away, and it takes 1 year to go around. Well, Venus is a little bit closer, okay? And it takes less time. Mars is a little bit further away and takes more time, okay? What about Jupiter? Can we find the t squared and the r cubed for Jupiter? What will the information be? Well, we're given the time for Jupiter. So in order to get time squared, we just take this number and we square it. That should be equal to the r squared number. Notice that all these numbers are pretty much equal to each other. And then we can do the reverse function to the third power to find the actual r on this side. Let's look at what that would look like. Okay. First off, put in the t is 11.86, so t squared is 141. Just like that. If t squared is 141, because that's equal to r cubed, that's also 141. Okay? And so to get this number here, I just basically take the cube root of that, and it ends up being 5.2. All right, Kepler's laws apply to any celestial body orbiting any other celestial body. All the planets going around the sun, any moons going around planets, any satellites going around the planets, and even the rings around the planets all follows Kepler's laws of planetary motion. It was phenomenal because back then the telescope was not even invented. In summary, Kepler's laws of planetary motions follow some basic mathematical principles. The first law simply states that all orbits are in the shape of an ellipse. Number 2, there is equal time for equal area. So the object that's in orbit will speed up close to one of the foci, the one that's causing all the gravitational pull. Kepler's law number 3, the square of a planet's orbital time is equal to the cube of the semi-major axis. Yeah, thanks for listening. I'll see you in the main room. Bring any questions you might have.